State machines are obviously a useful abstraction in embedded software, but also in software in general. And so mbeddr supports state machines directly. Here is an example, the flight analyzer state machine. To better understand it, let's take a look at the graphical overview. We can visualize state machines by selecting visualize or pressing Ctrl-Alt-V. You can also show it shows here the transitions and the guard conditions. You can shorten that to only show the transitions. That typically improves the layout a little bit. You can always you can click on the labels here and it selects the respective element in the code. So that's actually a useful integration here. So let's look at the state machine, or at state machines in general. What do they have? They have states. Then they have transitions within the states. These on things are transitions. Transitions are triggered by in events, and then they, in addition, are only fired if the guard condition is true. And of course, the guard condition can access the parameters that you pass into in events. You also have out events, and these out events can be raised or sent using the send statement here, and they can optionally be bound to an external function. Like in this case, the function raise alarm is called if we send the crash notification event. State machines have actions. Here is an exit action, meaning it's executed whenever the before flight state is left. There is an entry action right here, which is executed whenever the state landed is entered. And then there is also transition actions, which are executed if this particular transition is executed. In addition, state machines can have local variables, so you don't have to represent counters as separate state or something. Okay, so let's see, what else do we have? Well, this state machine here is verifiable, which means that you can verify it. Let's see what happens if we do that. So by default, a whole lot of verification conditions are checked. For example, whether every state is potentially reachable, whether every state's transitions are deterministic, meaning that for each state, for each combination of in events and guard condition values, there is only one transition that is ready. And then we also check that all states and all transitions are potentially reachable and not dead. Now, here one seems to have failed. Let's look at the airborne state. It says that in the state airborne, for the speed, when the speed is 201, it is not deterministic what's going to happen. And of course that's true, because 201 is bigger than 200 and it's also bigger than 100. So I guess we should refine this to say that TP speed must be smaller or equals 200 meters per second. So that seems better. Let's rerun. Okay, it is still failed. Now it is for the case that the speed is 101 and the altitude is 0. Let's see, where does this come from? So 101 would be, well, it would be this guy, right? And it would also be, it would also be this guy, the speed, right? And of course, the way it is written is that this implies that the more specific constraints are checked first, but that's not how the model checker works, and you cannot always assume that this is actually what's going to happen. So actually what we want to say here is that the TP altitude is bigger than 0 meters. Okay, so let's see. So I think you get the point, right? Creating a correct state machine that works in all cases isn't that simple. And having a model checker that makes you aware of the potential problems is extremely helpful. So let's see if we've kind of fixed it. So there is seems to be another problem, and that's if the speed is 2 or 1 and the altitude is 0, and that is of course because we also need the altitude check right here. So that would be TP alt bigger than 0 meters. And well, I don't want to spend too much time here, and it's probably going to be fixed now. So having the model checker is very useful, and as you can see, by default it checks all these kind of automatic properties, but model checking also involves that you can specify additional properties. Now success. And you can do that by going to the verifiable attribute itself and adding additional verification conditions. You can say that you expect something to always be true, something to be true after something else has happened, and so on. And that's a catalog of about 15 to 20 reusable typical verification conditions that you can use. So that's the verification stuff. We also have hierarchical state machines. If you scroll down, here's the hierarchical flight analyzer, where you have composite states, and composite states can contain yet other states. Let's look at the picture so we understand it better, right? So here we have the somewhat shorter version. Let me just get rid of this stuff and make it bigger here. And so you can see the airborne state now has the flying, landing, and landed substates. That's of course interesting because you can now modularize the actions, right? So this airborne has, where are we? Right, this transition here, that is valid for all substates in airborne, right? And so of course this makes it much simpler. It's actually this transition here, right? Okay, so finally, you have to have an ability to interact with state machines from regular application code. We've already seen how the state machine can call out into C functions by using the out event binding. But you can also do the other way. Here is a test case, for example, where we instantiate the flight analyzer state machine to a variable f. You can instantiate it many times. You can then initialize it, and then you can interact with it by sending events into the state machine. And of course, you get the usual code completion, right? You only see the states that are valid for that state machine. You can then check whether it's in a certain state. There's also, specifically for testing, is a specific shortcut notation where you just send in an event and you assert a certain state. So, state machines, very useful abstraction. They are types, they can be passed around, they can be instantiated, and of course you can mix them, in this case, with the physical units. And there is also a possibility to embed state machines into components. We haven't shown that here, but that's possible as well.